Welcome back, everyone. In this video, we're going to talk about logarithmic functions. To get us started, we're going to use this example to motivate the topic and see why we need these logarithmic functions. All right, so our example is asking us how long would it take for an investment of $6,000 to double if it was deposited into a savings account with an annual interest rate of 8% and that interest is compounded continuously. So to help us set this problem up, we're going to need to remember our interest rate formulas, especially that one for our interest when it is compounding continuously. And the relevant formula is A is equal to P times E to the power of R times T. So remember, with this exponential model or formula, P is the principal or initial amount we are investing or depositing into our savings account. E is Euler's number, that special exponential base. It is just a constant here. R is our interest rate expressed as a decimal, and T is representing time. And the left-hand side of our equation A is going to be the amount in that account, or what that investment is worth after so much time T has passed by with this interest rate R and a principal investment of P. All right, so if we go back through our problem statement, we can see that our initial starting amount for P is going to be $6,000. Our interest rate R is 8%. And remember, if we're using this formula, we have to express it as a decimal, so 0.08. T is our unknown. That's what we're trying to figure out. How long does it take for this amount to double? And so if we want the amount to actually double, then eventually we're going to need A to be equal to twice that initial amount. So 2 times 6,000 will give us A equals $12,000. All right, and so now if we put all this information into our equation, A equals P times E to the RT, we get 12,000 is equal to 6,000 times E to the power of 0.08 times T. All right, and so now this is the exponential equation that we need to solve in order to answer this problem, and we can only take this equation so far. Really, the only step we can do at this moment is to divide both sides by 6,000 in order to isolate our exponential. So that just reduces this equation down to 2 is equal to e to the power of 0.08 times t. And now this is not one of those exponential equations we can solve using a technique like equating bases or anything like that. So in order to solve this exponential equation, we're going to need to introduce a new tool, what we call a logarithm. And so all a logarithm really is the inverse of an exponential function. And so just remembering the fact that this relationship between a logarithmic function and an exponential function is that they are inverses of each other will tell us a lot about these logarithmic functions. Because everything we learned previously about inverse functions is now going to apply for a logarithmic function related to an exponential function. All right, so the big idea is that logarithms are inverses of our exponential functions, and with that big idea, we can start to write down a more formal and useful definition for our logarithmic functions, because the main uses for our logarithms, at least initially, are going to be helping us solve exponential equations. All right, so there's going to be some technical criteria in our definition that'll make a bit more sense later on as we work with our logarithms more and more. But let's go ahead and read our definition now. So for x values greater than 0 and b values greater than 0, with those b values not being equal to 1, the function f of x equals log base b of x, that's how we read this notation, or y equals log base b of x, right? Just depending on if we want to use our y or f of x notation. So we call both of these the logarithmic function with base b. And so this is our notation for these logarithmic functions with a base of b, right? The base of our exponential is going to help us determine the base of our logarithms, right? Because if an exponential function has a different base, it's a different exponential function, so it's going to have a different inverse exponential function or a different logarithmic function corresponding to that base. And so what this logarithmic notation is really doing is just inversing this equation. So if we write y equals log base b of x, what that means is that if we were to take b to the power of y, that would be equal to x. And so we're going to be doing quite a few things with these logarithmic functions. There's going to be all kinds of properties to remember and work with. So there's going to be a lot of information to take in. A helpful thing to remember, a mantra you might want to kind of say to yourself is, what is a logarithm? All a logarithm is, or all that comes out of a logarithm, is an exponent. A logarithm is the exponent we have to raise the base to get a certain output for our exponential function. So if we say y is equal to log base b of x, right, y is the output of our logarithm. What is the output of our logarithm? It's the power we have to raise our base b to in order to get x, where x is that value we want our exponential function to be equal to. And so when we're talking about an equation in this form, like y is equal to log base b of x, we call that the logarithmic form. Or maybe just the log form of the equation for short, and that is equivalent or interchangeable with this equation, b to the power of y is equal to x. We call that the exponential form of the same equation. So these two equations are equivalent. The left over here is the log form of our equation, and to the right, we just have the equivalent exponential form of the same equation. All right, so that initial interest rate problem was just an example to help us motivate logarithms and see why we're going to need to use them. We'll get back to examples like that later on. And so next, I want to look at some examples of making sure we understand how to switch between the logarithmic form and the exponential form of one of these equations. All right, so to get started, maybe let's just try to evaluate this logarithm. Here we have log base 2 of 8. All right, so 2 would be like the base of our exponential. 8 would be equal to x if we were trying to change it into exponential form, and y is what comes out of our logarithm. So what comes out of our logarithm is going to be the power we have to raise our base, in this case 2 to, in order to get the number inside of our logarithm. That's like our x value over here. So to answer this or evaluate this, what power do we have to raise 2 to in order to get 8? And well, if we remember our powers of 2, it's going to be 2 to the power of 3 gives us 8. And we can check this or rewrite this equation or relationship in its exponential form just by switching things around. So log base 2 of 8 is equal to 3 if and only if 2 to the power of 3 is equal to 8. Here we have the logarithmic form of our equation, and down below we just have the equivalent exponential form. And so these logarithmic functions are just inverses of exponential functions. They're a bit weird and take a little bit of getting used to. And I think part of that is because it's an inverse where we can't really define the inverse function using some of our basic operations like multiplication, addition, subtraction, and division. But this isn't the first time we've ran into an inverse function like this. Right, if we were trying to find the inverse of a quadratic function like y equals x squared, well, we had to introduce a new function that helps us do that. That's what we called the square root function. And along with that square root function, we introduced some new radical notation, our square root notation. Right, we can't evaluate a square root function or find the inverse of a quadratic function using our basic operations like multiplication, addition, subtraction, and division. Instead, we have to create this new kind of operation or function. That was that square root function. The exact same story is taking place here. It's just now we're not trying to find the inverse of a quadratic like y equals x squared. We're trying to find the inverse of an exponential function like y equals e to the x or y equals 2 to the power of x. But the point is, we kind of need this new notation to help us work with this inverse function. All right, let's go ahead and look at another example like the one we just saw here, but maybe let's go ahead and try to do the notation in the opposite direction. So start with something in an exponential form and rewrite it in its logarithmic form. All right, so here we are starting with this exponential equation that says 5 to the power of 3 or 5 cubed is equal to 125. And now we just want to translate or rewrite our exponential equation in its logarithmic form. And so we can go down to our formulas here and just figure out what is y, what is b, what is x, and move things around. Or we can just remember what the logarithmic notation is really trying to describe. And so the base of our logarithm is always going to be the same as the base of the exponential equation that corresponds to it. So that'll be the logarithm of base 5 in this case. What goes into our logarithm is going to be the output of our exponential function or equation. So that'd be 125. And what log base 5 of 125 is equal to, or what comes out of our logarithm, is always going to be an exponent. It's the exponent we have to raise the base of our logarithm to to get the number inside of our logarithm. And this is telling us, well, we have to raise 5 to the power of 3 in order to get 125. That's exactly what our exponential equation above was describing. All right, so now that we've had a little bit of experience switching our logarithmic functions to their exponential form and the exponential equations to their logarithmic form, I want to talk a little bit more about these kind of technical criteria within our definition. So we have this requirement that x has to be greater than 0. And here we're thinking about x as maybe initially the input of our logarithm. Remember, our x has another interpretation if we take that logarithmic form of our equation and convert it to the exponential form. In the exponential form of our equation, that x value is representing the output of our exponential function. And remember, our exponential functions always have positive outputs. That's why x has to always be a positive number. It comes back to this inverse relationship between logarithms and exponentials. The input of the inverse function is the output of the original function. And so the output of our exponential functions are always positive, meaning the inputs of our inverse functions or logarithmic functions also must be positive. The other little technical criteria we had here was that b had to be greater than 0 and not equal to 1. And this just goes back to remembering that b is the base of our exponential functions. So always wanted positive bases so we don't have to worry about complex values, right? If the exponent is some weird fraction, we might end up taking like the square root of a negative number. So making sure our base is positive avoids that altogether. And the other condition is that we don't want our base b to be equal to 1, because if it is equal to 1, that's the most boring exponential function, right? 1 to any power is just going to be equal to 1. So that's not really an exponential function. It's really a constant function. That's why we don't want b to be equal to 1. And so as I mentioned earlier, the base of our logarithm, as that changes, it's going to change the exponential function that it corresponds to. And so there's infinitely many different types of logarithmic functions because there's infinitely many choices for bases for exponential functions, but there's really two types of logarithmic functions that we're going to encounter or work with the most, and those are what we call the common logarithmic function and the natural logarithmic function. And so we have these two most popular types of logarithmic functions, the common logarithmic function or common log, and the natural logarithmic function or natural log. And so all the common log is log with a base of 10, and it's denoted in a kind of different way. So normally with our logarithmic notation, as a little subscript right to the right of our log, that we denote the base. And so if that subscript is missing, if you just see log of x, that means we're talking about log base 10 of x. It's such a common logarithm that we don't take the time to write the base in there. All right, and the other really popular type of logarithm is what we call the natural logarithm, and that's denoted as ln of x. Think of like natural logarithm of x. And so what ln of x is, or the natural log of x is just log with a base e of x. And the reason why we use the natural log so much is because, well, we end up working with these continuously compounding interest rate problems where the base is e. Although once we get to calculus, we're going to see this natural log is actually the most convenient and best log to work with. And so because we end up using the natural log the most in calculus, we're going to kind of favor this one and try to use it more often than the other bases.